My name is Brian Hirano. I work for Micron. You might ask why Micron or a memory company would be interested in AI. I hope you know the answer to that question. And why would we be involved in this kind of AI hardware software co-design? It's very interesting to be able to somehow meld some of the hardware stuff and the software stuff to be able to decide where the future is going to go. And as you guys know, AI is a big thing. AI with the size of the model is a big thing, and so it impacts not only the hardware side and the amount of power and capacity and things like that. It also relies a lot on the software innovation or some of the things of Chakra that Tushar was just talking about. But anyways, we're going to talk a little bit about what we mean by this polymorphic architecture. So this is the kind of the goal that Ritu is alluding to, is what we term internally as the kind of the architecture that we're trying to drive here, that Weifeng is leading our group in. So format, we're going to do some introductions, going to give an architectural overview, other stuff. Hopefully you guys are engaged enough that you'll ask some very pointed questions to our very distinguished panel here. Don't want this to be runway, so please sharpen your swords and get your questions ready. With that, I'd like our panelists to introduce themselves. They've been involved in this. We do have one very special guest who impromptu, like at the very last minute, agreed to join our panel here. So we'll just go in. Why don't you go start, owner? Since you came in early, go ahead.
Okay, sure, yeah. Yeah, I'm not supposed to be on this panel, but they asked me to be on it this morning, so now I am. I'm Onur Mutlu. I'm a professor at ETH Zurich. I'm on sabbatical here at Stanford, as that says. I work in computer architecture, memory systems, storage systems, genomics, a lot of things.
My name is Weifeng. I'm the leader of this AI co-design work group. I'm currently a chief architect and the VP of software at Lightelligence, basically building system architecture and software infrastructure for optical computing and interconnect.
Danny Moore. I'm the director of product management and product marketing at Rambus, where we're focused primarily on the disaggregated memory interface, CXL primarily being the protocol of interest there. Before that, I was involved heavily in PCIe switching and switch fabrics and interconnects. Pleasure to be here.
Hi, Allan Cantle. My initial background is I was a pioneer in FPGA computing about 30 years ago and made a lot of progress in that area. So I guess polymorphism has been a part of my career over the years. Today, I'm the technical lead for the OCP High Performance Compute subproject, where we're actually building a very configurable modular architecture for computing with energy efficiency and sustainability as a core driving vision.
Hi everybody, I'm Tushar Krishna. I'm a faculty member at Georgia Tech and also currently visiting faculty at MIT. I broadly work in ML systems, focusing a lot on communication and communication fabrics, and I also look a lot at designing simulation infrastructures for next generation systems. Yeah, thank you for inviting me to be on the panel. Thanks.
Well, yeah, as you can see, we have a very distinguished panel here. A lot of people with gray hair like myself. So anyways, we talked about this polymorphic architecture. So I thought it'd be, a good thing to be able to level set. So Weifeng, I don't know if you can see the slide here, but oh, there it is, down at the bottom. So what is this thing called a polymorphic architecture, and how is it going to help and save the world here?
Okay. I have a short intro in the morning in the FTS update. So basically, this polymorphic architecture is the white paper we wrote from AI co-design work group. So the basic idea behind this is really inspired by two questions. The first one is, how do we build efficient architecture to scale with the faster evolving AI algorithm? Right? We all know the AI is changing so quickly, but building the architecture behind this AI itself probably really left behind just because the design itself takes maybe 2 years of cycle, but the AI algorithm probably changing in months. So it's really important question to answer. How do we make the architecture scalable with the fast evolving architecture algorithm? The second one is basically how do we take advantage of this the currently ongoing architecture innovations. For example, the latency bandwidth of the interconnect is really improving quickly during the past few years. And then how do we, let's say, build in this architecture, how the architecture should be reshaped if we give, let's say, near zero latency of interconnect. So with these two questions, and then we build this so-called polymorphic architecture really to address these challenges. First of all, with this, let's say, near zero latency of interconnect, essentially it doesn't matter where you put all the computer resource on the same board or on the same chip. It can be like distributed anywhere just because the latency itself is no longer that important. And that's kind of like the major motivation for us to invent this so-called polymorphic architecture. The second one is we want to really make integration easier for us to, let's say, take advantage of the latest architecture innovations like heterogeneous computing, system disaggregation, chiplets, and compositable memory, and all those good stuff. Right? With this architecture, then we can basically make sure that our future architecture can be easily, doing the resource partitioning, recomposition, decomposition, so that they can adapt to the current running applications. So that's basically we make sure that adaptability is the key component of this architecture. That's basically the most important idea behind this architecture.
So you have another buzzword in there. It's like fractal. What do you mean by fractal? What is always fractal there? I'm gonna put you on the spot.
The fractal computing is essentially it's kind of we imagine that system has like a different layer of the resources. For example, from the bottom layer, it's like a chiplet, right? Then using a chiplet, you compose a chip or SoC and a system and a rack and beyond, right? So basically, you can understand this as different layers of the computing resource. The fractal computing means at every single layer, we are able to do this composition, transformation, and adaptation, so that we have essentially we building this architecture. It's like a continuous composition and decomposition with all the resources, so that we have this kind of composability and the transformability for the entire architecture. So it's easier to adapt to any algorithm we would like to process. So that's basically it's just to put it simple, that fractal computing essentially is a continuous transformation and composability across different hierarchy of your computing resource.
All right. Well, thank you very much. So I'm just going to pull up the panelists again. So I'm going to ask questions, not put the questions on the screen, but just to remind you who these people are. And unfortunately, there was one person who couldn't make the panel. He was invited. His name is Vijay Reddy. He's a professor at Harvard. He couldn't make it because of a family emergency and had to bow at the last minute. But I was going to channel him to kind of talk about some of the things that Ritu talked about earlier, and her talk about the size of these models, like the growth, like the parameters. If you look at GPT-3 to GPT-4 to BARD and everything, the number of parameters and the size of these things that are going on right now. And so Vijay Reddy, why I wanted him on this panel is that he was a member of ML Commons, and if you look at his name, you'll see that he's both on the ML Perf original benchmarks for training as well as for inference. And so he has this very broad perspective of training and inference and the amount of data that needs to go in training, and is actually participating in other benchmarking activities. But for our panel, everyone knows about large language models, but there's kind of two sides to the largeness problem. One is the size of the models. The other is large number of users want to be able to use these models or multiple models. So you have large models and you have multi-tenancy of perhaps the same model, perhaps different models. Which one are you most concerned about in terms of an overall system architecture? Can't all hand it over to owner.
I'll take a stab.
Go,
I mean, I think, and I tried to touch on this a little bit in my composability talk. From looking at traditional AI, it feels to me like the focus was on the model size specifically, because the model is loaded onto the accelerator of some kind. the inference occurs based on user input and an output is provided. And there, the memory subsystem is constrained really by the model size. With LLMs and generative AI, we start to see that the demand on the memory subsystem is really a function of the input token length and the size of the output being generated. So it's constantly varying. And when we talk about multi-tenancy, previously you could have user 1 send some input data, get its inference response. User 2 could send its input data and get its user response. Meanwhile, the underlying memory subsystem can simply contain the same model. Now, when we talk about generative AI, we have to maintain this context. The context that I'm using as I'm trying to, generate output out of say ChatGPT is different than user 2. And so when I go to generate my response, or I see my response and I maybe want to ask a follow-up question, well, now the data on that particular accelerator for me is different, even though someone else is using the same LLM. That they're generating a different context because they're asking different questions, they're asking different follow-up, and so that KV cache needs to slide out of the accelerator memory, and now user 2 we need a whole new set of context. And so from my perspective, whereas before it was really the quote unquote model size itself that was dictating a lot. Now the model size is still obviously critical because that has to come in and out of the accelerator memory, but the context switching between multiple users also becomes ultra critical because now it's like almost the whole model needs to flush in and out as the different users with different context are generating new information.
All right, thank you, Danny. So in the interest of time, let's take a vote. Who's more concerned about the size of the model over the multi-tenancy, like the number of users using the models and different models?
Say
size model?
Size for me.
Size matters. Is that the number? And anyone more concerned about the multi-tenancy issues? Go ahead, Owner, please.
I don't need to pick a side, I think, on this battle, but I think I'm concerned about both. I would say.
Please do.
I mean,
I'm trying to divide us, Brian.
Yeah, you're trying to bait us. Yeah, I think in the end, capacity is important, right? You need to store it, but clearly, without users querying the model's capacity is not important in that sense. So I think you need a combination of both. But the challenge I see is as the capacity grows and as the number of users grows, you want to really provide both capacity and bandwidth to serve these things and the latency. So I think you need really a balance between those. Like as capacity grows, performance should also grow, which is not necessarily the case in existing systems, I think.
That's right.
Just to add to what Owner said and Danny said, right? I think it also depends, as we said, on the use case. So if you are focusing on training, then the requirements from the system would be, so this large model, obviously you need the memory capacity. You are sending these large collectives, you need a lot of bandwidth from your fabric and so on, right? But if I'm looking at, let's say, an inference use case, this kind of comes to, as Danny said, right? Now in the inference use case, different users, I have to worry about latency a lot more. I also have to worry not just about model size, but also things like KV caches, which need to be stored. So there's other constraints that will come in. And similarly, I think, and if you kind of look at the fine-tuning use case in the middle, which has become very, very popular these days, again, there's interesting kind of trade-offs where I am still training the large model. Maybe I can use techniques like LoRa to just train a subset of weights. I don't need these large data sets. So again, it's interesting that you kind of have different system requirements. If you're ultimately designing one system for all three, then yeah, that's where I guess a lot of the polymorphism that that we heard about also comes in. Yeah.
Yeah, I would be concerned both. The large language model size is critical for this architecture to resolve. So that is something the architecture itself has to give performance based upon this, whatever the size of the model. But for the multi-tenancy, I think the polymorphic architecture itself actually has implied a solution for this already. Just because when we have this resource, partitioning and recomposition, essentially we are building a logic processor for every single user of this resource, right? So that means to each of the tenants, and they have their own separate logic process already. So whether we have enough resource to accommodate so many tenants at the same time, we could either, if we have a sufficient physical resource, the partitioning and recomposition itself already form every single logic process for every single tenant. But if not, at least we can do like a time sharing for the single process as well, because the polymorphic architecture is able to readapt itself on the fly. So that's the implicit solution from this architecture.
One thing I would say from the size perspective is, obviously, the bigger these models are, the bigger the memory footprint, the higher the bandwidths, and all the rest of it. So and things get further apart, and we burn more power on all of these. But we've also got the idea that maybe we can split this into many smaller models with very specializations rather than one large language model. And so, okay, that means, so is there any benefit into those smaller models? So you almost know what the question is, and you target to a particular specialty model. And is that going to be more efficient to do that? But then you've got other models being idle if they're not used for that type of problem.
Right. So I was actually going to pivot over to the power discussion since, as you point out, Allan, is like more capacity, more bandwidth. Sounds like more power to me. And as long as I've known you, you've always been like very cognizant of power utilization. Could you riff more about power and how you see like the current trends and how the sustainability? I think we had that discussion too about that, and maybe other techniques like you're talking about to sort of mitigate the power utilization, be it for these large language modules or any other training and inference.
Yeah, I think there's two angles to that. The way we do it today, I'd like to start with a reference model. And then the reference model is our brain. So we all know that that's about 20 watts. And if we just look at, just use Frontier as a baseline, I know it's not necessarily a great AI machine, but if you say 100 petaflops is roughly the capability of the brain, that's 2 megawatts or thereabouts of the Frontier. So we've got, what's that, 5, 6, 7 orders of magnitude of difference. So that's a tremendous opportunity we can do a lot of optimization in my mind. But that said, we need to think about this in two ways. Our brain is always doing inferencing, but it's also doing training when we're asleep. So the way the brain goes about it, and also we learn a lot of it. You're fairly fixed, our networks are, from when we're born. You've got to start with a fixed network, and it takes many years. We've got millions of years of evolution to get the network, whereas these big machine learning machines are doing really serious training. So you can see they're learning very fast in compared to the evolution of the brain. But on the inference side, do we really have 1.7 petabytes or whatever it is of memory? So we're missing a trick here somewhere. Switching over to the way we are actually doing it today, we do have this problem of it's a computing memory problem, and the bandwidths, the capacities, the latency wants to stay low. Everything's getting to, we want infinite everything or zero latency. And the problem is that data movement is where we burn power. And so what memory solutions are going to give us the best footprint? And that's possibly where I'm coming in with smaller specialty models where maybe HBM memory is the most power efficient, relatively speaking, to bandwidth, etc., but it doesn't have the capacity. So if you could split it into smaller models that can stay relatively tightly coupled, you could get a big win in power. And that sort of analysis, I guess the biggest thing that I've been pushing in our OCP HPC is our industry just doesn't think about power and energy efficiency. You look at a block diagram of any computer architecture and say, how does my decision on this architecture get affect the power efficiency? And we don't have a clue. Now, that said, ASIC designers, they're always concentrating on the power of their particular block, but as a macro level, if I'm planning an architecture, a solution, we have zero tools. So we need the industry to put energy efficiency first in the architecture we're building, software and hardware, of the computers we're looking at.
So you mentioned something very interesting, talking about the memory and the how close it is to compute. And so there's things that owner has personally found and did a lot of seminal work in the area of processing in memory, processing near memory, whatever you call it. So owner, how can some of the technologies that you and your group have thought through for PIM can be applied to something like AI, particularly in AI in a data center?
And that's a good question. I definitely agree with what was said earlier. I think moving data around is a big cost, and that has been shown in many works that occupies a lot of the energy and also time. But time we can fix with other things, but energy of data movement is very hard to fix. Before answering your question, Brian, maybe I should say I like this polymorphic description that Weifeng mentioned earlier. I think in terms of polymorphism, we should probably have computation also distributed across any possible component that we have in the system. Currently, we have a huge bottleneck because you have to go through almost all of the components to take the data out, whatever you're doing. Large language models do this a lot, to an accelerator somewhere, or to a CPU, wherever you're doing the training or inference, and everything else does nothing but moving data. Right? If you look at this, I definitely agree with what Allan said. We don't consider energy in our systems, and absolutely we don't consider energy or balance in the way we design systems today. And I think we need to break that barrier. Now, how do we actually, can we take advantage of this? I think absolutely yes. Like there were talks earlier from in one of the sessions, I think SK Hynix and GSI, they were talking about accelerating LLMs using near DRAM or in near SRAM computation, and they showed good results. I think we need to do more, and we kind of need to break the mindset of compute should be done in a compute unit, and compute should be done everywhere, storage, memory, and once we do that, we distribute the computation around, and we find different ways of actually scaling the system. Maybe others have any comments.
I think this is great, and I think there's been efforts around compute and memory compute, like in the fabric, but fundamentally there's always, and we've just talked about compute, network, memory, right, as very distinct components, and trying to distribute compute, make it more pervasive would be very valuable. Of course, I understand there's technology limitations for things like this, like you can't just put compute inside DRAM the way DRAM is designed. You can't just directly put it in storage. But I think if we can address, and that's where actually I personally find the chiplets very promising, because now you can kind of have a substrate where you have compute and memory kind of strewn around, and as long as you have a very nice fabric to connect everything up, you should be able to very quickly get to another compute unit without having to go all the way to the CPU. I do feel like there is of course a software challenge here, which I'm not an expert on, but the fact that you have now compute all over the system, how do you schedule things, even today, load balancing is a challenge in a system like this. What would that mean? I mean, those are things that I feel are open questions, but again, very, very important questions to solve. And I think that will certainly address a lot of the data movement challenges.
Let alone what are the architectural guarantees in the system that allows the software to schedule things appropriately. So
actually, just on that point of load balancing, with compute is actually pretty cheap. A CPU core, I believe now, is probably virtually free. They used to say a transistor is free. There's so many of them, right? But a CPU core is virtually free now. So if you put a CPU core where every piece of data is even sort of very cold data, and you can send a request, maybe that CPU doesn't get turned on for a year, but once it gets a request where it's relevant, it says, okay, I'm going to light up, and I'm going to do that local search on this local piece of storage very energy efficiently, and then I'm going to shut down for another year because it's a forensic operation or something, then that's good. The compute is not being used hardly at all only when it's needed. But when you think of it as being free, relatively speaking, to the storage in the data is where the money goes. But we all think about CPUs being the expensive part. So we got to change the thinking as well.
So Danny, actually I listed you. It's funny we're going down this path because it's kind of opposite of the question I want to ask you, which is the disaggregation. And in some ways we're talking about bringing things closer together, but disaggregation is moving things further apart. So can you drive the disaggregation?
Yeah, I was listening to everybody talk, and I mean, I absolutely agree, right? Power is such an important piece, but then everybody always wants to, have their cake and eat it too, right? And so, they want composability. We want all of those things. We want to disaggregate the memory interface because we like the idea of pools and optimization at those levels. But then you do pay a bit of a penalty, right? As you disaggregate and you move those interfaces off of, where you had a single piece of silicon before, now you've got multiple pieces of silicon, your memory interfaces, across the data center or, on the top of the rack or, all those sorts of things. So I think we have to keep it in mind. We do need that composability, and really I think the polymorphic architecture that we're talking about really does rely on that level of composability. But there can still be some we can still maintain power as one of our KPIs or primary design targets. And like Allan was saying, if we think about optimizing where that compute is, that maybe then right now our composability is like compute is here and memory is here. But if our composability is more fluid like that, more fractal like, more polymorphic like, then we can have smaller amounts of communications between nodes, or optimized levels of communications, and therefore achieve kind of both, right? The composability and some power optimization.
Right,
but in the meantime, there's going to be some pain points. Absolutely.
Right, so pulling in those AI hardware, software co-design buzzwords in there. But, I think we did talk about, the number of panelists talked about how you balance the system depends on the kind of workload. And so to you, Tushar, Tushar and I are involved in like 4 different areas regarding Chakra. And I think it's a really interesting tool. If you have not looked at it and you're involved in AI and performance, you should look at it. But how do you think, Tushar, that we could use in this working group the Chakra model to help perhaps identify and maybe make some decisions based on information that's gathered from Chakra?
No, actually, that's a great question. In fact, I think it ties literally to the couple of points that came earlier, right? Like, we would fundamentally, like from a software level, okay, we have some compute operations, memory operations, and communication, right? But where we do those, right? Like, do we actually have a disaggregated system which is easier to optimize, versus do we actually have compute everywhere, right? And so then I kind of start viewing this as, again, like a kind of a scheduling problem where algorithmically we need to do these things, we need to have some data that's stored somewhere, and ultimately, how do we map that onto the substrate? And I think that's where tools like Chakra, I think, or like frameworks like this would help, because they are trying to, abstract out what the workload needs from a system perspective. These are the computations I need to do, and at the granularity, which is agnostic of the underlying system, right? It's not individual instructions where I already know this is x86 and these are the instructions, right? Like, it's a granularity of these are the compute operations, these are, the kinds of, again, at least in AI, we know we are moving around tensors, right? So these are the tensors that need to ultimately be brought in, or the computation needs to be performed on these tensors, and ultimately, like, this is the kind of communication we need to do. Ultimately, just algorithmically, I need to add up n things. So, that's a reduction, right? So once we have things at that granularity, I feel like I think what would be very valuable is then trying to design tools to see where that computation can be run, what would be the costs. And again, I think if we have models that really take not just performance, but also energy into account, we'll then be able to make clever decisions on which parts of the system really need to be how we design them today versus which parts can actually, get to a rethink, right? And I mean, just as a simple example, right? Like if I have some operation in memory which I know will fit in a certain block, I could really go with a PIM-like approach. Like one of the challenges with, PIM-like architectures often is, well, if I have to, swap out, what is running there, that's expensive, right? But if I know that this thing can really fit there, that makes a case for a PIM-like architecture. I'm hoping that, frameworks like this will allow us to make decisions like this.
And Chakra is both for training and for monitoring
Yes,
inference.
yes. So
right?
I mean,
that's
it's
the key.
ultimately like it is whatever workload you're running, which could be training, inference, fine-tuning. Yeah.
Okay. So in the interest of making you available for the block party at 5 p.m., I had a number of other topics, but I'm going to switch to one hopefully controversial topic, which will hopefully, at least will garner a bunch of different opinions. So, there's a whole bunch of press and discussion around security in AI, confidential computing, confidential AI, and things like that. So I was wondering if each of you can talk, at least add your perspective in it based on your experience and your area of expertise, and how either through hardware or software or process, view the security issue with respect to AI training and AI inference.
Anyone?
Security experts here.
All right.
Go for it.
Okay, maybe I'll generalize the question. I think this is very important. So it's not just a security issue in my view. It's certainly a privacy issue, which is related to security, but it's maybe a safety issue also, depending on where you use the AI. I mean, I don't see AI as just LLMs, even though they may be the current type. I think AI will be everywhere, and it's going to make decisions for us, and it's going to affect every aspect of our lives, right? And I see perhaps clearly there are security issues, like these should be making decisions that that someone doesn't manipulate, for example, for a bad purpose. But safety issues may be more common with these, especially devices that are employed at the edge, right? And if you get, for example, some robustness problems, reliability problems, bit flips, it's not clear if I'm going to trust my self-driving car, which is probably the AI that I interact with most closely, right, in my life. So I think this is a critical issue, and we should probably put a lot more emphasis onto these robustness issues in general: safety, security, reliability.
Yeah, and to add on to that, again, it's one of those items that we want our cake, and we want the cake and eat it too. Security adds complexity, encryption adds latency, and all of these things that are sort of roadblocks to efficiency, right? But absolutely, right? These are things that we need to consider as we build our architectures going forward. And in particular for AI, it's going to be privacy. I know for me, I'm from Canada, so I have to pass through the American, the U.S. border, and the cameras know who I am, and I'm just like, how do you even know that? But so it's one thing for the U.S. government to be able to, I don't know, read the retinas in my eye, but then it's another thing if that level of capability can be integrated into a $50 camera, then all of a sudden everybody can have access to that type of information. So it is very important, the privacy aspect as well.
Anyone else?
Yeah, I was going to add, actually, I think Danny brought up this interesting point, right? Again, as system architects, it is like, so we all agree, yes, privacy, security should be part of these systems, but there is a cost. And it's important to understand the cost, right? For example, if you're familiar with things like, fully homomorphic encryption, right? So that's great, right? You can compute on encrypted data, but if you start running FHE with ML, like very simple things like activation functions like ReLU, which is really, just, a very simple operation in hardware suddenly becomes very, very complex, right? So essentially, we're already talking about compute memory challenges for LLMs, and now if each of these operations becomes, orders of magnitude more expensive, but provides, guarantees, again, it's not very clear, right? And people may still end up going with the approach that is cheaper, both for performance as well as for energy, right? All of these things are expensive. So I think we do need to invest in understanding techniques. Maybe there is, again, a granularity of safety that can be provided. And again, I think it's a wide open area. And again, I'm very excited about what will happen, but also scared because, yes, as I said, my worry is that a lot of times business decisions will go with what is cheaper and efficient rather than, just secure. So I think that's something we should be careful about.
Yeah, I probably can look at this from a different perspective. And the secure computing, security definitely is important, but we can look at the security from different angles. For example, secure computing, it's basically make sure that all the computation is done inside a secure enclave. That is something which is being supported inside the Intel CPUs and maybe other processors. But we also have a difficulty because whenever we transfer the data from one processor to another, then either the data will be encrypted and then basically you pass encrypted information on the fly. But the trouble is we have to do encryption, decryption, and then everything is done inside, inside the secure enclave. It's very slow. So the performance is also important to customers. So that's why a lot of actually customers, they sacrifice the security in order for them to achieve the performance. So in one, I think from the checkout case, that certain abstraction of your model is important here. For example, if you have this a lot of convolution kernels, and after a few layers of the convolution, probably you are not able to identify the original information anymore. So from that point on, maybe instead of just trying to do the secure computing inside the, let's say, secure enclave, and then you can maybe just run that as a plain data on the GPU. In that case, you're able to accelerate this secure computing without sacrifice the security. So there was a lot of things can be done here. And certainly in the polymorphic architecture, we are able to, let's say, leverage in this secure processor in this entire framework, and hopefully passing the information back and forth with like an abstraction of your model rather than trying to do encryption everywhere.
So does anyone have a pointed question for our panelists here? Either something we talked about or something that... Gene, go ahead.
Crazy question. This is a crazy question, but it'll be simple because I ask short questions. But we're talking about mechanical electrical systems, and you guys were talking about how to do things differently. And you were talking about 20 watts for the brain. What about chemical systems that would, a different methodology, because we're kind of reaching the wall on classical electronic systems? That was fast. What do you think, Allan?
Reservoir computing, surrogate models, all these kinds of things that are kind of more analog based. Right?
Well, I think that certainly we do need to go back. Is it called neuromorphic computing? They're saying that traditional, what we're doing in AI today is really gone on its own tangent. And I'm no expert in this, by the way. But this neuromorphic computing is really going back and studying the brain more and trying to say, can we learn from how that does it? Obviously, we've got a lot of research going on the analog AI. We've had a few dead ends, and some people predict it's the wrong way to go. Others are still I've seen some very interesting progress. We'll see where that will go. That could bring some tremendous benefits. I think one of the things, actually, to our point of errors, the human brain has a lot of errors, and often disastrous ones in driving cars. But also, actually, it's very resilient to those errors. It's very fault tolerant, and to that extent, how can we're trying to make our computers so precise all the time and never make mistakes, but how can we maybe architect our computers so that we are more fault tolerant in the computation, and does that bring more efficiency or not, is the case maybe. But the chemical approach, obviously, I think there's a lot of insight there, because if you understand how the neurons work, it takes, our neurons fire at about between 10 and 200 hertz or something like that. So we're extremely slow. For a message to get from the brain down to your muscle at the bottom of your leg is, you're in the millisecond territory. Yet, when you watch a tennis player play tennis, they are unbelievably quick. So the brain is the eyeball's literally wired to the muscle on the leg. It feels like there's a fast path, and the body is rewired, the neurons are rewired for that. And so I think there's a lot of learning to come from it, but I'm not sure if chemical approach is the way to go, but maybe.
Right. Well, just.
I mean,
I was going to refer back to you anyways, Otis. So go ahead.
no, I mean, there are people working on it. That's actually great. There are papers you may have seen on chemical computing and also biological computing. I think these are great efforts. My feeling is there should be a lot more effort in this area spent in these different paradigms for computation. I don't think we're doing enough, frankly. We're looking at new electronic technologies. That's great. Quantum, that's great. But I think the amount of effort spent on emerging paradigms is very, very disproportionate, I should say. I mean, that said, we probably also don't quite understand how existing systems behave. We probably don't understand how chemical and biological circuits behave, but without experimentation and evaluation, people actually trying to build these things, we're not going to get anywhere without understanding, basically. But I believe, I should say, we do a lot of work on analog computation in memory. Clearly, that's very different from chemical. And I see a lot of promise and we see a lot of good results with analog computation, especially in energy efficiency, but also performance, exploiting the parallelism. I believe if you can actually figure out how to do computation biologically, chemically, we can do probably much better.
So I'm going to close this up by saying that we're probably not going to include a bucket of water or a box with chemicals in it as a part of the polymorphic architecture. But Weifeng, I'll let you close since you're leading our group and talk a little bit about summarize everything and put it in the context of this polymorphic architecture we've been talking about.
Maybe I'll just make this as a call for actions. And currently, AI co-design work group is in the second year now. We are working on the definition of the architecture and also leveraging the framework which Tushar invented, AstroSim, to do the simulation at this point. But in the next year, we plan to do more like a FPGA type of prototyping and a software stack. And we are also looking to expand this into resource pooling to enable large-scale polymorphism. So we definitely need a lot of strong community support to look into the individual component, for example, like this transformable architecture, reconfigurable interconnect, composable memory, and lots of stuff we need to get a contribution from the community. So I would encourage everyone to participate in this AI co-design work group, and any passing the information around to your friends, colleagues, and welcome to this AI co-design work group. Thank you.
Great. Thank you very much. Enjoy the block party.
Thanks, Brian.
Thanks,
Thanks,
Brian.
Brian. Yeah.